let's look at our first graph, graph A. Suppose that a car moves a distance of 40 meters over 5 seconds. Now, to calculate the speed of the car, we need that change in distance. Let me use this one. That change in distance over an amount of time. And to find that change in distance, it means that that rate of change in distance over time is shown by the gradient of the graph, our speed. So, speed, distance over time. So to calculate our gradient, we need the change in distance over time. Now, the car moves for 40 meters, and it moves for 5 seconds. 40 over 5, that's 8 meters per second unit. So the gradient of the graph is 8. So since we are looking at the change of distance over time, that means that gradient represents the speed, which will be 8 meters per second. The problem now is that this gradient that we have will not always be linear. Even a car will never just be moving at a constant speed. Sometimes our graph will be curving like this, and then we will have different gradients at different points. Suppose there, suppose there, suppose there. If we again suppose the distance over time, we can see that our car moves from rest and then the speed changes as we move along the graph. Now, to calculate the rate of change of speed now, we are going to have to calculate the gradient of the graph. You can see that it's different at different points. Here, it keeps changing and changing as you move along the graph. Now, another thing to note is that when I wrote the formula there, I said the change of distance, but I did not say the change of time. So when we always calculating the rate of change for something, we look at the rate of change of distance over another variable, the rate of change of one variable over another variable. We call that differentiation. Now, in the last graph here, at point A, let's look at how the gradient changes as we move along the graph. And we do this at tangential points. A tangent is a line that touches a curve at one single point. Now at A, our gradient will be very steep. At B, it must touch the curve at one point. That's basically nothing. That's me walking in this room right now. At C, now, I don't know if a slope going down and a slope go, which one is hard, because I usually find it difficult coming down a mountain than going up. So we know that this gradient will be negative. At D, another tangential point, this straight line must touch at one point. So if this again was our distance over time, as time goes by and you go through the graph, that means there will be change in speed, there will be change in the rate of speed until you reach one point there. We shouldn't let it get vertical, because then that would mean that the gradient does not exist. Your calculator will show you an error there. Okay, now let's look at D. Suppose we have a graph with a changing gradient as we move through the graph. Suppose we put a point there, 8, and we want to find the gradient at point A. Suppose we just took it here for fun. Now, to get a picture of the gradient, we're going to put a tangent. Again, a tangent is a straight line that touches the curve at one point. I'm a human, I won't be accurate there. So it only touches at point A. Now, we can get a visual of this gradient that it will look somehow like this. But to calculate it, it would rather be more complicated than that. So to make it easy for us, let us introduce a point B, and this point must be very close to A. Suppose we are taking a very small section over here of this graph, and we exaggerate it so that we can make it more easier to analyze. Now, this point B, let's connect it using a chord. Using a chord, this chord has its own linear gradient that connects the 2 points, and this gradient, it is not the same as the gradient at point A. But now, like I said, since this is a very small section there of A, and we made a point just for the sake of calculation, this vertical part will just show us that there's a very small minute change in Y, and this is a very minute change in X. Now, what we're going to do now is try to see, as this point B moves closer to A, moves along the graph and approaches A, this gradient of the chord AB, as B moves closer to A, the gradient of the chord will get even closer to the gradient at A, because this gradient over here will turn and turn and turn as B moves there, moves there, moves there, until we get the gradient of A. So to calculate the gradient of the chord A, we are going to look at the change in Y, the change in the vertical, the change in the vertical, change in distance. So we are going to change in Y over change in X. We call that rise over run. Rise over run. Rise there, run there. So in this graph, this is denoted by the small change in Y over the small change in X. Remember that now B, we try to move B closer to A so that the gradient of the chord gets closer to the gradient of the tangent at A. Now, this change in Y, let me show you the little chalk. We cannot let it get to 0, because then the division by 0 will not give us a value that we want. So we try not to get to 0, but try to approach A as much as we can. This distance, as it reduces, we try to get as close to A as possible, but not let the change in X be 0. Because we cannot let the small change in X reach 0, we will only consider the limit as the small change in X approaches 0, but does not actually become 0. So that means that this value will approach 0, but will never be equal to 0 because of our graph there. Now, let's take the same idea where we have point A and we want the gradient at point A. Now, to visualize the gradient at point A, we are going to draw a tangent, a point that touches A once. Yep, that's our tangent over there. It shows visually the gradient at that point. Now, to make our calculation more simpler, we're going to add a point B and then connect the 2 points using a chord. Let's add that chord again. Now, remember the idea is that B is only such a small amount away from A. So there's only a small change in Y and a small change in X. And we're gonna look at how this point B approaches point A and how the gradient of the chord moves as it approaches A until it can give us an approximation of the gradient at point A. So since we have a graph of Y equal to 2, the coordinates of A, the X value will be this 3 if you take it, use the B as the reference point, it means that it has moved only delta x amount to get to A. So we have 3 plus delta x, and then for y equal to x squared. So to get our y, it will be 3 plus delta x but squared. Now let's look at our gradient. We found out that we can get a gradient by changing in y, delta y over delta x. Let's use our values now. Now change in y. Our value of y, 3 plus 5 3 plus delta x squared minus the y value of b, which is 9, over the x value of a, x and y, 3x plus delta x, 3 plus delta x minus the x value of b, which is 3. Now let's simplify this quickly. We'll have 9 6 delta x plus delta x squared minus 9, all over 3 minus 3, we have delta x. Now 9 and 9 are gone. Let's take out a common factor at the top. It will be delta x. We'll be left with 6 plus delta x over delta x, and divide, and then we get 6 plus delta x. That is our value. Actually, now remember that this point B is moving towards A, and as point B moves towards A, this delta x approaches 0. So as delta x approaches 0, then 6 plus delta x approaches 0, so we'll get 0. But remember, we do not allow it to become 0, it only approaches it. So we are looking for a limit. We write it as limit as delta x approaches 0 of delta y over delta x is equal to the limit as delta x approaches 0. Delta y over delta x, we found that it is 6 plus delta x. So as delta x approaches 0, that means we have our gradient as 6. That is the gradient of y equal to x squared. What I'm going to do now is take the same example and just do it with variables and not give a and b actual numerical values. Now we still have a over there and b over here. We're looking for the gradient of a. Gradient at a. We're still connecting a and b by chord AB. Chord AB. And now the value of b is x, and we're using the same function y equal to x squared. So x will be x, the x value of b will be x, and the y value of b will become x squared. Now the values of a. Remember, we're still observing as point B approaches point A, so that we can take this gradient of the chord as it approaches the gradient of tangent at point A. So the value of A, the x value, this point will move there, so the x value will go from x plus this delta x. So x plus delta x. The same way we have 3 plus delta x, because it was 3 and then it moved to A and became delta 3 plus delta x. The value of y will be the x value squared. So the x value x plus delta x squared. That's our coordinates for A. Now let's find the gradient here. So we look at change in y over change in x. Change in y we find it by taking the y value of a, which is x plus delta x squared, minus the y value of b, which is x squared. Now, that change in x will be the x value of a, which is x plus delta x, minus the x value of b, which is x. We simplify, we have x squared plus 2x delta x plus delta x squared minus x squared over x minus x. We are left with delta x. Now x squared minus x squared, we will lose those and then take out the common factor. Sorry, little camera issues, but now if we take out the common factor here, that is delta x, and we are left with 2x, and here we are left with delta x, and our denominator we still have delta x, and then divide, we are left with 2x plus delta x. Now if we want the actual gradient now of the tangent here, we are going to look for the limit as delta x approaches 0 of 2x plus delta x. This is delta y over delta x. Now remember, we said that as the point B approaches A, delta x becomes small and approaches 0, and as it approaches 0, that means our limit will be 2x. That is the gradient at point A. Now that means that if we have a function y equal to 2x, if we differentiate it, we get 2x. Now that means 2x will be the gradient at a certain point in the graph y2. If we are at point x equal to 3, our gradient will be 6. That's why when we were at point x equal to 3, our gradient was equal to 3. Now this new function that we get, we are going to call this the gradient function or the derived function. We denote this in this way. If f at x is equal to x equal to x to the power 2, that means that the derived equation will be equal to 2x. Now, what is nice to notice about this, let me come back. This value here came down here. It came down here, and then the value that is left here is subtracted by 1. So the idea is that to find the derivative of x equal to a, you will be left, it will become a comes here, ax